So now we'll talk about an idea called thread. It's a very important idea, so pay attention. You will hear this word number of threads again and again. So very loosely you can understand thread as it's just one worker or one unit of work that is being performed by one worker, and it's a light amount of work typically. Very loosely speaking, I mean it can be anything. So if you are parallelizing a code, you will have multiple threads that are being created, and then when the work is done, they are being destroyed. So whenever you want a parallelizable work to be done, you will summon some threads, and these threads will be executed hopefully on different cores. But threads are independent work that are being performed mostly by different cores, but you can have more number of threads than the number of cores available. It's just that then each core will deal with multiple threads, but thread is that parallelized or individual amount of work that's being allotted to some worker, but you can allot multiple amounts of threads to the same worker as well. Okay. So as I said, threads, and what does a thread have? Thread has its own program code. It will have its own registers that it can deal with, some data. So some amount of register, some amount of L1 cache will be allotted to that particular thread. So different threads will have different registers, L1 caches for them, or part of those. And even, I mean, not just one code, but if you talk about whatever is happening in the background, if you look at Chrome, for example, sometimes you see that you have opened 10 tabs, and if you look at taskbar, you see 10 different Chromes running. So there are 10 different threads that you see for each. So each tab actually becomes one thread that is being executed. So that's parallelized work that is being created. Okay. So as I said, typically it's lightweight, but that is not necessarily included in the definition of a thread. So we'll be using this term again and again. So that's the reason we're defining it. And threads can be created and destroyed very quickly. So in the sense that, let's say you have a loop, you are running a program, then you reach a loop. Okay, and then that loop has a lot of work. So that work can be parallelized. So each iteration of the loop is independent. Each of the work iteration is independent. So you can split it into threads, and these threads can then, depending on the hardware you have, can be executed on different cores, hopefully at the same time, and then they can be, again, the result can be combined and the result can be put into different memory locations, and then the threads are destroyed. So that work that was created during the loop, once the loop is over, is gone. So that thread can be, they can be spawned or created and destroyed when the computation requires. So languages or paradigms like OpenMP will use this idea of creating and destroying threads during the program. That will help you parallelize the work. Next is not next, but these threads can have issues associated with them. So multiple threads can have access to the same data, okay, although they have their own registers, but the main memory can be shared. So what happens in that case is that we can get into these issues such as memory contention, okay, where two different threads are trying to write into the same memory location. Okay, so that can have problems. I mean, two different threads are writing to the same memory location, but depending on which thread writes first, the result will be different when you try to print it out. It's like, both of them are trying to modify the same variable x, and depending on which one will be able to complete the work first, which you do not know. It could be the case that thread number 1 for some reason is going slightly slower than thread number 2. So thread number 2 writes the value of x into the memory, and then thread number 1 writes it, but then when you print it out, you want it the other way around. Okay. So that ordering is something that we don't worry in serial computing, but in parallel computing we have to worry about it. If things are happening in parallel and each of the thread is trying to modify the same variable, then we can have these contention issues. So if there is a dependency, or if you are adding, the contribution of each thread is being added and then returned to the memory, so we have to be careful about these ideas. So there has to be some sort of a barrier to synchronize all the threads, and only then you proceed from there. Otherwise, if thread number 1 finishes first and it moves on in the code, but other threads are still working, then thread number 1 may use a variable which was supposed to be modified by all the threads. Like you are adding 100 numbers, so you break it into 10 threads, so each thread will add 10 numbers, and then they will contribute their numbers into the number x, and then one of the threads is using that x number for doing some other calculation. So you have to make sure that all the 10 threads synchronize first, and then you proceed. So you have to have some sort of barriers explicitly being put in the code. So you have to think about those ideas. So if you have multiple threads, then you may get into these problems. Now there is also a problem with cache coherence. As we said that if you have a variable sitting in the cache, let's think in serial computing, and you have modified that variable, it will not get written to the main memory until it is required in the main memory, or that cache location has to be used by some other. So you have to clear the cache. That means that whatever sitting in the cache will be written in the main memory. But let's say a variable x is being modified by one thread which is sitting with one core. So it's modifying that variable, but that variable x is still sitting in the cache. Now that x is required by thread 2 in core number 2, so it will try to extract that from the main memory, but it is using an outdated version of x. So what happens is that thread number 1 will have to write whenever thread number 2 requires x. Since thread x is sitting in thread number 1's cache, it will have to put it back into the RAM or the main memory, and then thread number 2 can take it from there. So what's happening here is that it's a very complicated situation now. So there's a lot of work that the compiler has to do to make sure that these situations do not arise where you end up using an older version of the variable. But these things can actually make programs slower, because if thread number 1 is doing something to the variable which is sitting in the cache, now it has to keep writing it back to the main memory because some other thread requires it during that time. So it could happen that the number of cache accesses and the cache and main memory accesses actually increase. So there is always a trade-off. So one has to understand those ideas as well. Is that clear? Okay, so please remember, and we'll talk about these ideas. Based on this, we'll have to place OpenMP program calls. Okay. So just be careful about cache this memory contention, synchronization issues, and cache coherence. Like we talk about threads, we also talk about process. Okay, so these words thread and process, they are not interchangeable. They can be used, but a process as compared to a general thread that we talk about has its own private memory space. Like we talked earlier that a process, two processes will not share memory. Okay. threads can share memory in general, but process particularly when we talk about it, then the shared memory is not available. So if you have to, you can in a computer while running a program, you can generate multiple processes, as we'll talk in when we talk about MPI, in distributed computing. So when you have different processes, then there is no shared memory between them. So if you want to send a variable x, use a variable x in process in process 2, where process 1 is working on x, they'll have completely different copies of x, right? They'll be physically different spaces in the memory. Each so process 1's x is different from process 2's x. Okay, so even if the code is the same, you may think that if I use x in process 2, but process 2's x is like they are doing work differently. They are running two different codes. So if process 2 requires a variable from process 1, it will have to request, or process 1 has to send it. So the send and receive will have to be done so that a variable is information is sent from one process to the other, because they don't have any shared memory space. So that results in cost in terms of time. So there's a lot of latency in sharing data between processes. So that can slow things down. But if you are dealing with large number of, if you require large number of parallelizable threads, then you have to go beyond a certain number, because you can only put enough number of cores on a machine. Beyond that, you have to have distributed memory parallelism. So for that, this information sharing is the only option. Even that, so there has been a lot of progress in terms of hardware to share information in a faster manner, but that again is a bottleneck. It's not as fast as if you had things available on a motherboard. Okay, so the processes communicate by passing messages. So MPI stands for message passing interface. It's mainly about passing messages or passing information, and this is how you communicate, and communication basically means sending variables in MPI. Okay, so in distributed memory, when we use multiple processes, there are some issues that we have to understand. So one is more complicated to program it, because you have to not just think about the algorithm, but you also have to think about when you have to send memory from which process to which process, and then the other process has to make sure it is receiving memory information from some other process, only then it can proceed. So there have to be send and receive calls inside each process's instructions. So it's a bit more complicated to program this. There's a lot more latency in terms of because of communication in distributed memory. So if you have a program which only requires a few threads, it's better if you have shared memory parallelism available rather than using distributed memory, because shared memory will be much faster. So there's an idea called fine grain parallelism versus coarse grain parallelism. Okay, I will discuss that in detail later, but you will hear about these words as well. So shared memory versus distributed memory. You'll also hear about fine grain versus coarse grain. So fine grain will be where think about while doing parallelization. It's like micromanaging things. You pick up a for loop. Okay, this for loop can be parallelized. So let's parallelize this. Let's give it to. Then you again have a for loop. Let's parallelize this. Okay, this looks like two people can do, two threads can do it. Let's distribute that. So that's a very micro way to manage things. So that's called fine grain parallelism. You finely parallelize the code. Coarse grain is, on the other hand, you think of the domain that you have. Let's say you're solving a problem of fluid mechanics, for example. You're solving the flow in this room, airflow in the room. So when I say solving, you mean you want to find the temperature and velocity of at different points in the room. So what I do is, if I have 8 processes available, I split the room, the volume of the room, into 8 parts physically. Okay. I decompose the domain, which is my room, into a certain number of parts, and then I say that okay, each part will be handled by a given process. So what happens is that whenever, I mean, of course, there is some interaction between different domains. Otherwise, no, the problem is trivial. So some molecules at the boundary of this domain is hypothetical in our computer, but the subdomain 1 will have communication with subdomain 2, because molecules of subdomain 1 are affecting molecules of subdomain 2. Particles are moving from 1 to 2, and there is some sort of diffusion happening from 1 to 2. So that way, that information transfer you have to think about how that will be happening. So this is called coarse grain parallelism. Rather than parallelizing each loop, you split the domain, and then you let each process handle the domain with some message passing that happens between the domains. So we will look at all kinds of codes. So OpenMP is typically suited for fine grain, and MPI is suited for coarse grain. But the way we will learn about things, I will teach you about, since we learn OpenMP in 5 to 6 lectures. So once we get that stage where we feel extremely confident with OpenMP, I'll show you a code which is coarse grain parallelized code in OpenMP, and then once we understand that, then we'll convert that to an MPI code. So that will be a smooth transition from OpenMP to MPI, rather than learning a new paradigm like MPI with a new approach of solving or writing algorithms. Okay, so we'll have this smooth transition from one to the other. Any questions? So it's worth revising this lecture. So what will happen is, in the next lecture, I think we have the quiz coming on 20th, right? So we have one more lecture before that. So I've kept that lecture for your problems, questions, and some ideas about Fortran. So I'll have half an hour of discussion on Fortran, some advanced topics left, and then the remaining 1.5 hours will be for you to ask questions. So please revise the content and utilize the next lecture for extracting as much information as you can extract out of me. Although I will not give you the questions for the exam, but this is actually very helpful. You tend to anticipate as many problems as possible. In that process you learn, and that is what my motive is, that you learn, and at the same time you get good marks as well. Next lecture will not be on parallelism, and then we'll have the quiz, and after the quiz we have one lecture, and then I think we have a break. Some vacations are coming. So in that one lecture after the quiz, we'll have a discussion on Param Himalaya, and then we will, once you are back from the vacations, well, not vacations, but that long holy break, then after that we'll have a couple of lectures on OpenMP. So they'll happen very quickly. So make sure that when you are attending those lectures coming back from the holidays, you revise these two lectures, today's and yesterday's lecture, so that you are up to date with these ideas. So these ideas are very intense, and you will now see that in the next feedback I will get, you'll say we are going very fast. Okay, because now we are at a stage where we understand programming languages and the ideas. Now we can start programming things too. So you will have to put in a lot of effort when you go back home to practice things as well. So there is one more topic I will discuss today, that's called Amdahl's law. How many people have heard about Amdahl's law? AMDAHL, Amdahl's law. No one? Now when we talk about parallelizing things, we have to think about, I mean, how much of a benefit you can get from parallelization. So one way would be that let's get some compute time, because we have some free compute time available. So let's put in 50 processors, 50 threads, and then see what happens. Well, that's a very naive approach, and I will not suggest you to do it because you are going through this course, but typically that is what beginners do. They just run the code with an option. So let's say there is a standard code that you have available. Let's run it with a minus j followed by 4 and then see what happens. Maybe that will be better. So let's send on the cluster and then get the results. Maybe it will be much slower than that, okay, much slower than serial code. So if you are writing your own code, you have to think about the algorithm. like how much of an algorithm is sequential and how much is parallelizable. Now sequential will make sense if you think about again simulations which are dependent on time. I have an initial condition like temperature and pressure and velocity of air molecules for today, and I want to predict the weather for tomorrow. So based on today's information, I will step in time and slowly predict the values of these field variables like pressure, temperature and velocities over time. So what that means is I cannot parallelize, I cannot split this iterations in time between different threads. I cannot say that let's do time 1 to 10 by one thread, 11 to 20 by the other, because the 11th thread depends on 10th, 11th iteration depends on 10th. So until those 10 are done, you cannot move to 11th. Okay, so this is a sequential code. Whereas if you are transposing elements of an matrix, well, you can do it in a parallelized manner. You can say that let's break into 4 blocks. Each block is handled by each thread, and this is an embarrassingly parallelizable problem. So some part of the algorithm will be inherently sequential, and some part will be parallelizable. So depending on what part, how much of an algorithm is sequential and how much of it is parallelizable, you will get some speed up. You will get some useful benefit from using multiple threads. So let's say this situation where 50% of the code is sequential and 50% is parallelizable, and you have a supercomputer available with you. How much of a speed up how much of a benefit in terms of improvement you can get if you can run it on a parallelized machine? Let's say your code takes 10 hours to run. So if I give you a supercomputer to use, what is the fastest you can run the code? Can you give me the result in 1 hour? The code is taking 10 hours. The algorithm is such that 50% of it is sequential, 50% is parallelizable. I give you the fastest supercomputer, the one at Oak Ridge. Okay. What is the fastest you can solve the problem? 6 hours. Any other answers? How many people say less than 6 hours? 2. Okay. How many people say less than 5.5 hours? How many people say less than 5 hours? How many people say less than 4 hours? You have a supercomputer with you. You cannot go less than 5 hours here. Okay, that's because we're talking in terms of speed up. So at most you can get a speed up of 2. Okay? No matter how many processes you use, you cannot have a runtime which is more than a factor of 2. Or less than a factor of 2, basically less than half of the runtime. So you cannot make it faster than twice. See, sequential part is 50%. So that means out of those 10 hours, 5 hours, right now you're running on a serial machine, right, just single thread. So half of the time is taken by, so let's say 10 hours, 5 hours are taken by sequential algorithm part, and the remaining 5 hours are taken by parallelized part. So if I give you infinite number of processors, all you can do is the latter 5 hours can be reduced to 0, because you will divide that by infinite. But the initial 5 hours, which was sequential, you cannot do anything to it, because one thing has to happen after the other. So that 5 hours, 50% of the part runtime is something that cannot be reduced because it cannot be parallelized. So this is what Amdahl's law states, that there is a theoretical maximum you can get. Of course, actual maximum, you cannot have infinite processors. If you use 2 processors, then you can reduce the remaining 5 hours to 2.5. So your total runtime is still 5 hours of sequential and 2.5 hours of parallel. So that's 7.5. So as I increase the number of processors in my parallelized part, I will reduce that time. And if that number tends to infinity, then the time tends to 0, but sequential part will always be there. Okay. So let's have a more realistic situation. 10% of the code is sequential and 90% can be parallelized. What is the fastest, what sort of speed up you can get in this case? Theoretical maximum. Six hours. What do you think? 1 hour? Oh, from 10 to 1 hour. Okay. Anybody else? So what is that speed up is? 10 by 1, that is 10 times. Okay. So think on speed up. It's taking 10 hours, now it's taking 1 hour. So you have increased the speed of the code by 10 times. That's right. So the maximum you can get is 10 times because it's a 10% sequential. So out of those 10 hours, 1 hour is sequential and 9 hours is parallelizable. So theoretically, if you have infinite processors, you can reduce that work of 9 hours to 0, but the 1 hour work is still there, you cannot do anything to it. So that will be required. So in general, if 1 by s of the computation is sequential and the remaining 1 minus 1 by s is parallelizable, then you can get at most a factor of s speed up. Okay, that's a theoretical maximum, of course. Practically, if Ts is the time taken by a serial machine, that's only one thread, and you use a parallelized machine with p processes or processors, then the time taken on a parallelized machine or a cluster is basically 1 by s times Ts. Then because you have finite number of processors, that's 1 minus 1 by s times Ts divided by p. Okay, so earlier we said this p is tending to infinity, that's a theoretical maximum. So this term, right hand side term, tends to 0. The first term is 1 by s, which was let's say 10% in the second case, that's 0.1 times Ts. So the speed up is this right hand side minus divided by Ts. Ts, because speed up is relative to the serial time. So Tp by Ts is your speed up. And that seems very trivial, but it's worth doing this calculation. In fact, I suggest that you plot this graph. So what you do is you plot P versus Tp. So you do a quick calculation in Excel. Do it. So you put the value of, zoom it in. So I'll say serial is 0.1 and then parallel is 1 minus 0.1, so that's 1 minus this. And then you plot the value of P, which is the number of processors. So we can just have a range of values of P, and here you can have the value of speed up. Okay, let's call it theoretical speed up. And then we also actual speed up. And then we also have a theoretical speed up. So theoretical speed up is just same for every it's for infinite processors. So that is going to be 1 divided by the serial, which is 10. So I'll just fix this, and then we just have this 10, and the actual speed up is now is the serial time plus the parallel time. So serial time is 0.1. Okay, Ts I am taking just 1 unit for now because I'll divide it by Ts, so that doesn't matter. And then the parallel one is this divided by the number of processes you have. Okay. So then you can just and then we'll just plot these. Hopefully that should result in something interesting. sorry, speed up is 1 divided by this, right? This is the time. Right. So now we can plot these. Okay. And then well, theoretical. Right. So this is your actual speed up. So you can see that let's have a few more processors here. Okay, so now what you can do is you can play around with this serial and parallel, and then that should help you understand. So if my serial code is 50%, so that's 0.5. So you can see that there's no point having 100 or 60 processors. Beyond a certain stage, beyond 10, you are not getting much benefit. So at 10 it's 1.8, and then the theoretical is 2. So that this even before running the program, you can plot this. If you have an idea of how much code is serial and parallelized, usually don't have that idea, but you can do some experiments to figure that out first, and then you can plot this kind of a graph and then decide. Because see, if you add some extra number of processors, it adds some computing some cost as well. Okay. So this is Amdahl's law. We will pick it the discussion from here when we talk about OpenMP. So thank you, and I will see you on in the next week.